Oh, ये नहीं आ रहा, माइक नहीं आ रहा है. हाँ, हाँ, yes. Good evening, everybody. हाँ. So, yesterday we have started and we have seen how a program executes, and we have seen the different phases of program development, like editing time, compile time, loading time, linking time. And we have seen the uh, attributes of a variable. And within that, we have seen the size and the range of a variable also. So we have covered few things in a different way, not like data types and then operators. We have not gone this way. We have gone the overall picture, how a program run. Major thing was that. And we had now, and that the important thing was activation records. So we have understood how the variables are created. Whenever the function is called, the variables are created, function ends, they are destroyed or deleted. So now based on that, we will understand the working of recursion. We'll start with this now. So as I have covered few classes earlier, so little bit of that will be repeating. Then after that, but in a different way, then after that, the things start very freshly. Okay, like yesterday few things were repeating, like previous class was there, but I have covered in a different way yesterday. So anyway, today, so we'll start with recursion. All right. See, we'll talk about recursion, what is recursion, everything later on. But before that, I will write down some piece of code and I'll ask questions. You have to answer the question. So just to confirm, what all I have taught yesterday, you have understood perfectly. Okay? Yeah. So here I have function main, and it is having its own variable, some a, b, and then it is calling one function called fun1 and doing something more extra and ending. Now, if you see what is function1, fun1, which is having its own variables, x, y, and it is doing some work, and it is calling one function called fun2. Then, if you see what is fun2, function2 is having its own variables. I can take same names also within the same variable names also, because but they will belong to only this function. Scope will be limited to this function only. And it is doing some work, and that's all. I have this program. Function main calling fun1, fun1 calling fun2 from here. Okay. So now my question is, if you run this program, total how many activation records are created? Total how many activation records are created? In the code section, the program goes in. Now this is a stack. So how many activation records are created? The first one is for main, yes. Then main is still running. It's having its variables a, b. Then it is calling fun1. So its activation record is created and it's having variables x and y. Then still function 1 is running. Then it will call function 2. So function 2 activation record is created. It's having variable x, y, and z. 3 variables are there. Then whatever they are doing, we are not highlighting, we are not looking at the statement, just we are looking at the function calls. So if you observe now, main first executed is activation record, it has called fun1, then fun2. Then how they are deleted? First fun2 ends, so its activation record is deleted, then it goes back to fun1. And inside fun1, after fun2, nothing is there. So fun1 also ends, its activation record is deleted. Then the control goes back here, next line, whatever the lines are executed, the remaining lines are executed, then main also get executed. So total 3 activation records were created. Okay. And what was the size of each activation record? If you want to study, you can study that. You can tell the size based on the variables that are shown here. You don't know what is the extra memory it may be taking, right? Because it has return address, it has a space for storing a result of the expressions and constants that we don't know. All right. Only based on the variables what are declared, you can tell the size. 2 bytes, 2 bytes, total 4 bytes. Anyway, so size we cannot guarantee for any activation record. So we simply count as one activation record. Okay, whatever the size may be. So total 3 activation records are created. Now, based on this, what is the total size of the stack consumed based on the number of activation records? Size of the stack is 3. Size of the stack is 3. So in this piece of code, the observation is total 3 activation records are created. And at a time, all three were there. So size of the stack required was 3. So these are the 2 points you can note down if you want to copy this one and write on the observation. Okay, then I'll show you some other code. Then we'll go on recursion. In previous class, I have used ABC. Now I'm using fun1, fun2, fun3 to make it look a little bit different. So maximum size of the stack was 3. 3 activation records, not bytes. 3 activation records, whatever the size of the activation record is. Based on this point, gate questions are there. Means number of activation records created. They will not ask how deep, they will say how deep the stack is going. 3. They'll ask mostly upon recursion. There are some gate questions are there that are from data structures. If this recursive function is called upon a graph, what is the depth of this stack? Like this type of question is there. What is the depth of this stack? So it means how many calls it is taking, means how many activation records are created. Okay, understood this one. Now let us move on to the next code. I'll write down one more piece of code just to ask you some questions. Here are some variables I, j, and k, and it is calling one function called a, then it is calling one function called b, and doing some work and over. Now, if you see function A is having some variables, let us say a and b, then it is doing some work, then it is calling one function called b, then finish. Then if you see function b, it is having its own variables, let us say pq, and nothing else. Now you have to tell me, you can draw the diagram by yourself. I will not draw it. Just you have to tell me total how many activation records are created. One for main, then A, then A is calling B, A is calling B, then B ends, control come back to A also ends. Then if you go back to main again, it is also calling B. So B is called twice, one time from A, one time from B. But, acha, one more thing here, one more thing. Okay, okay, let us finish this. Total how many activation records are created? 4. 4. Then one more question. What was the maximum size of the stack in terms of activation record? No, no, no. You draw it and tell me. Draw it and tell me. Now everybody draw it and tell me. Not sure, 3 or 4. So draw it and tell me. Maximum at one time, total how many records are required? 3. Yes, 3. Size of the stack required is 3. At a time, maximum 3 are there. So maximum size of the stack is 3. See, first, I will draw it like this. First one is mains activation record is created. Then above that A, then above that B, then B ends, A ends. Then again it is main is still there, so it is calling B once again. So what was the maximum size? Total 3 only. Total 3 only. And total activation records are 4. Then B is deleted, then main is deleted. Total 4. Size of the stack is 3. So this is also important. So what is the maximum size required is important. Total how many are created? Created, deleted, not is problem. But maximum size required is a problem. Now one thing here. Function B is called from A as well as from main. Okay. So when it is called from A, it has to return back to A. When it is called from main, it has to return back to main. So where a function should store its return address? Inside the activation record. See, when first time when this was created in this activation record, it was having the returning address of A. When it is called from B, in this activation record, it was having the returning address of main. Right? So last class we saw that a function will have its return address stored inside it activation record. It should know where it has to go back. From somewhere it is called, so it has to go back to the same place, call our function. So this is over. Now let us talk about recursion. See, you have seen that one function can call another function. One function can call another function, right? The same way, I have one function here, void fun, which is taking some parameter n. And here, if n is greater than 0, then it is printing the value of n. I'm not writing printf, just pseudocode I am writing. Then it is calling itself with n minus 1. This is an example of a recursive function, right? Recursive function. See, you have already seen that one function can call another function, right? So same way, let us look at this. This function, if you enter in, it is taking a parameter n. I'm reading it. Follow this one. Taking parameter n and checking if n is greater than 0, then it is printing the value of n and calling another function. Calling another function. You know, function can call another function, right? So don't think that is the same function. Think that's another function. So it's easy to understand recursion. So what is that another function? Same only. So this time, suppose whatever the value of n, suppose from here, if I am calling this function by passing 4 was passed. Now it is calling some other function by passing 3. So it is actually calling same function by passing 3. So again, 3 is greater than 0, print 3, then again calling some other function by passing 2. So which is that one? Same function only. So here, actually, function calling itself. If a function calling itself, then it is called as a recursive function, or it is the process is called as recursion. A function is called as recursive function, and the procedure is called as recursion. All right, function calling itself. Now, one more thing. Over, this is over. Now, one thing. I'll write on the function once again. Void function fun, which is taking a parameter n and print n, then call fun of n minus 1. Is it a recursion or not? Recursive function or not? Yes, it's a recursion. It's a recursive function. All right. Now, you know, whenever a function is called, activation record is created, right? So for this function, how many variables will be there in the activation record? One variable, that is n, whatever the values pass. Now you tell me what happens to this function. Huh. Activation record is created for fun one. Then again fun, again fun, again fun, again fun. Is there any termination point here? No. So what happens? Activation records are created, keep on creating in the stack. So that at one point, stack is always limited. It is not unlimited, it's limited. At one stage, stack overflow. Stack overflow. And when the stack overflow, your function will suddenly stop and your program will also stop. Program will also stop. All right, crashing of a program. Stack overflow will cause crashing of a program. It is just like you are driving the car, suddenly car stopped. It's a crashing of a car. Suddenly stopped. All right, so this problem arises. Now, same thing, will this also cause the same problem or it will stop at some point? Stop. So this condition will stop this one. So this condition is called as base condition. This condition is called as base condition or termination condition. Termination condition. Base condition or termination condition. That's all. Now I have defined recursion. Only two things about recursion. A function calling itself is called as recursive function, and every recursive function must have a base condition. Must have base condition. Over. Two things. Now if there is no base condition, what happens? Stack overflow, your function crashes and the program crashes. Yes, infinite loop. We don't say infinite loop, Tarun. We say stack overflow only because it's not a loop. Yes, when a function is called, then only activation record is created. Yes, very good. Yeah, the problem was no base condition and it will cause a stack overflow. If it is loop, we say infinite loop, but it's recursion, we say like infinite loop never stop, but no problem with the stack. But in recursion, as activation records are created, it will be keep on creating. At one stage, stack will full and it's overflow, so stack overflow. Over. Now, I'll remove this one. Now, the most important thing for answering gate questions or understanding the code is you should know clearly how to trace recursive function. And you must trace every recursive function that you will be coming across in your course. So in examination, you do it directly. But here in the classroom, you must trace everything. Because if you miss anything, you will go get a wrong answer. All right? So you should keep on practicing. Then later on, just with your eyes, you can do it. But don't do it with your eyes right now. Okay? You draw it. You draw it. So now I'm showing you the most important thing that will be useful in all the subjects. Oh, sorry. C programming, data structures, and algorithms. In all three, this is useful. How to trace a recursive function. So I'm showing you, watch this one. So when you want to trace a recursive function, you have to draw a tree. You have to draw a tree. And along with that, one more thing I'll tell you. If you have to trace and see the working of a loop, you have to draw a table. So I will write down here. Tracing. Tracing means going through line by line, dry running it, or going through line by line and see how it is working. So when you are tracing, recursion, for that you will use a tree. And if it is loop, then you'll use a table. Table. What all the variables are there in a loop, used in a loop, you write them in the form of a table. For every iteration, you go on changing the values step by step. Now for recursion, you should draw a tree. With a tree, you can clearly get it. You cannot draw a table for it. So now we are drawing a tracing tree of a recursive function. Tracing tree. So we want to see what is the output of this function, how it works. All right. So if I am passing 4, you know the answer. What's the answer for this one? 4, 3, 2, 1. Okay. But we will trace it and tell the answer. Trace it and tell. So when I'm calling the function for first time, okay, function 4, when I'm passing function 4. So 4 is greater than 0. Yes. So what are the steps that it has to perform? First step and, okay, I'll just change the color here. Step 1 and step 2. It has to perform 2 steps. So when it has to perform 2 steps, you should draw 2 branches from this one. As many steps you draw, that many branches. So first step is first print. Print what? 4. Then second step is what? Call function with value 3. Now it is freshly called. So whether this function, first function has finished? No, it has not finished. It is calling function once again, okay, with a new value. So this is a new call. In this new call, n is 3, 3 is greater than 0. Yes, it is true. So it has to perform 2 steps, first step, second step. So first step is what? Print 3. So print 3. And the second step is what? Call itself with the reduced value of n. N is what? 3. So pass it 2. Again, a fresh call is made. N is 2. So 2 is greater than 0. So yes, it is true. There are 2 steps. So first step is what? Print 2. Then call itself with reduced value of n. N is what? 2. So it will pass 1. 2 steps. Then again fresh call is made. Now this time n is greater than 0. Yes, greater than 0. So it will perform these 2 steps. So first step is what? Print. Then again call function itself by reduce value of 0. Reduce value of n. This time n is 0. 0 is not greater than 0. So it will not enter inside this if block and ends. So this simply terminates. Doesn't do anything. Doesn't do anything. Right? So this function fun of 0 has done nothing, has finished. Now when this has finished, it will go back to the previous call. In the previous call, only 2 steps were there. Both the steps are over. Both the steps, first step and second step is completed. So this will also finish. And it will go back to the previous call. Again, 2 steps, both the steps are over. So this will finish. So it will go back and this will also finish. It will go back and this will also finish. It will go back and this will also finish. So this is how we draw a tree. See, first step was printing, then step was this one. So if you follow this one, first time it was printed 4. Output, if you see, first time it has printed 4, then made a call. Then printed 3, then made a call. I'm just giving a comma here. And printed 2 and made a call. Printed 1 and made a call. For 0, nothing was done. So this is the output we got. And if you want to see how it is happening inside the main memory, how the activation records are created, then this is the code section. Okay, this is the code section. Now, first time, okay. Main I am not showing. I'm not showing main. Main, you know very well that main is there. So first time, fun of 4 is called. So I'll just write f of 4. All right. Then second time, okay, f of 3, oh, sorry, okay, fun of 3 is called. Then next time, fun of 2 is called. The next time, fun of 1 is called. The next time, fun of 0 is called. 0 finished, this activation record deleted, deleted, goes on. So total, what's the size? Remove main. So total how many? 5. Size of the stack is 5. How many calls it is making when you pass 4? Total 5. Now, look at this one. Look at this one. When you pass fun of n, Total how many calls? N plus 1. N plus 1 calls are made. Total N plus 1 callers. Stack size. What is the stack size? Equal to the number of calls in this case. So it is N plus 1 only. Over. Wait a minute. Last one more thing show you here. If you want to see what is the time taken by this function, what is the time taken by this function if you want to see. So time taken means how we find out the time means what? See, I'm assuming you don't know what is time complexity. I'll just explain, okay? See, suppose, what is the time taken for moving this chair into that room? One chair, time is 1. We don't want watch time. Because if I am moving, I may be moving slowly. If you are moving, you may be moving quickly. We don't want exact watch time, 3 minutes, 2 minutes, 1 second, 5 seconds. We don't want that. For one chair, 1 unit of time. Now for one bench, 1 unit of time. So when we want to measure the time, we don't want actually watch time. Just we want the rough estimate. All right. So for moving one chair, 1 time is taken, 1 unit of time. 2 chairs, and the chairs. Are you getting me? This is how we measure the time. Now, let us go to dinner, for dinner now. What will be the cost? Per head. Okay, how many? 30 members are there. 30 into something. Okay, how many people are going? Some N people will be going. So what will be the cost? N into whatever it is. So the idea is, as you increase the number of heads, the cost will increase. That's the important thing we want to understand. Analysis. है खर्चा कितना आएगा? जितने लोग होंगे उतना आएगा. Right? More people are there, more cost. So how much time it for moving a chair? As many chairs are there, that much time. So general idea we want to get. We don't want exact watch time. So whenever we say time complexity, we want to just get the idea. We want to visualize how it is. We don't want figures. So time complexity means just getting the idea. All right. So let us go back to this. We want to see what is the time taken by this particular function. So let us see what it is doing. So if you observe, okay, sorry, yeah. If you observe, it is checking a condition. Okay, I'll cost it as 1. For checking a condition, 1 unit of time. So like one chair, 1 unit of time, one bench, 1 unit of time. We are not looking at the size also. So let us say every statement takes 1 unit of time. You got it now. Every statement takes 1 unit of time. This statement is bigger, this is smaller. Okay, we don't want that. What will be the cost? Per head cost. He is fat, he is slim, he eat more, he eat less. No, we don't see that. Just rough idea we want. Okay, same way. One statement takes 1 unit of time. So I'm including condition also. Okay, now this line printing 1. This is also 1. So total how many steps are there? 3 steps are there. So 3 is what? Constant or linear? Constant. When you have a figure, it's constant. When you have a figure, it's constant. Now, I'll tell you one interesting thing. What will be the cost for the dinner in a hotel who is charging 500 rupees per head? If 3 people are going, 1500. No, 3 people are going. 1500 only. Constant. Now, how many people are going? Some N people will come. N into 500. Now, when you're not sure, it's N. When you're sure that this much is the figure, constant. Constant doesn't mean that, so constant means same price, always same price. That's the meaning of constant. Understood? So whenever you have 3, it's constant. Now, once again, you have to tell me whether it's constant or not. A hotel will charge 500 rupees per head and 10 people are going. 5,000. Constant or linear? Constant. When you know the figure, it's constant. Understood? Got it? Now I'll explain it. Slowly I'll explain why it is called as constant. Later on, again, you will see some other way I'll show you. Okay. Now let us not go that much deep now. So we will say 1 unit of time, 1 unit of time, 1 unit of time. Usually what we do, we don't consider this. We just see this statement. If that is true, then only these are executed. Nah. So we'll consider these two only. So now it is 2. It's your choice how much you want to count. Okay, going to hotel means how will go, cab na, cab cost also. You keep it aside, just see how much the bill will be. No, petrol is also, we are burning petrol also, fuel also. Don't consider, that's how much you want to go in detail, that is on your choice when you are doing analysis. You want analytical result, you don't want exact figures. All right, so what's the time now? Constant. So the function is taking constant time. Means what? Order of 1, order of 1, order of 1, order of 1. Now you tell me, every call is taking how much time? Order of 1. Now total how many calls? N plus 1 calls. For 4, 5. 5 is constant or not? We say order of 1. If you say 5, order of n. So for n, for 4, we say order of 1, right? For n, we say order of n. Exactly. So the time taken by this function is how much? Order of n. And the space in the stack is also n. If you want to say order of n, you can say order of n. All right? That's all. So what all you have observed, you can make the notes. In this function already you have taken tracing tree is important, and the stack contents are important. And because you may not be drawing this always you may not be drawing this, but tree is important every time. Now, finding the time is also important. Finding the time is also important. A plus t of n minus 1, 1 plus t of n minus 1. Okay. It's not A, you can make it as order of 1. Keshav, you can call it as order of 1. Because A is defined, we have 2 or 3. You say 2 or you can say 3 also. And it is constant. So for constant, we say order of 1. So t of n minus 1 plus order of 1. Then order of 1, you can write it as just 1. So actually it is order of 1, but usually we just say 1 and then keep on solving that one. That is about recurrence relation. But I'll not cover right now. The topic will be too big. I'll be mixing too many things together. Just I wanted to show the working of the recursion. So also I have to show the stack. Along with that, we have seen the calls, how many calls are there and all. All right, finished. Now, let me tell you something about this order of n. Okay. I have to continue with recursion, but as we came across this, I'll tell you a little bit more on this one. Then later again, we will see this detail. So just a introduction to part. See, actually, when we want to find the time complexity of any algorithm or any piece of code, we want analytical time. We don't want watch time. All right. So when we are getting analytical time, when we analyze and try to get the time, we actually get a polynomial or exponent. So usually we get polynomial. Okay, the time will be represented in the form of a polynomial. So what is a polynomial? Is it a polynomial or not in terms of n? What is the degree of this polynomial? What is the order of the polynomial? No. Degree you said 2. Next question, order of a polynomial. 2 only. Order is also 2. Degree or order is the same thing. It's a synonym. Degree or order is same. So I'll say O for order. Shall I write just 2 here? Doesn't make sense. Doesn't make sense. Let us write n power 2. Now, if you see other way, sir, what happened to 3? What happened to 4n? Why you remove all of them? Why you are removing? Why you are just taking n square? No, I am showing degree. So degree is how much? 2. But just writing 2 doesn't make sense. It doesn't give the clear idea for us. Okay, so let us write it as n square only. And let us say degree of or order of n square. It's making sense now. Got it? Understood this one? Got it? This is the notation followed. Notation. Notation means symbol or a language, a symbol followed for showing the time. Actually, we are not interested in O, N, all these things, brackets, everything. Just we want degree 2. Acha, N square. Degree is 2, high. Degree is 3, more higher. That's what we want. But to show it on paper, we write big O of N square. So we are writing highest term. That's it. Understood? We are just interested in degree. Now, let me show you more. Okay. So for this, I'll say big O of n square. I'll write one more function, f of n. 3, sorry. 3 means again you may get confused. Always coming 3. 7n plus 10. What is the degree? Or order? 1. 1. So we don't say 1, we say big O of n power 1. What is big O omega? That is a different story. Leave it. So say O. Order of O. Following till here? Now, one more function, we got the answer as 8. y1. Watch this. Watch this. y1 I am showing you. Why we say 1 always, I am showing you. Actually, it's 8 now. Sir, 8 it was, you made 1. Sir, it was 8,000, you made it 1. No, we are talking about degree. So see, n power 2, n power 1, n power 0. N power 1, n power 0. This is what? So what I should write for this one? Big O of anything whose power is 0 is? That's why we write 1. That 1 doesn't mean, sorry, that 1 actually means n power 0. We are writing the degree n power 0. So n power 0 we never write. So we make it as 1. So we are writing what is there beside 8, right? In terms of polynomial, we are not concerned about 8. We are in concern about degree. Degree is 0. So instead of saying 0, we say, n power 0. N power 0 is nothing but 1. That's how it's becoming constant. Understood this one? Constant. Yeah. We go off 1, we go off 1, we go off. So whether you take it or not, that's your choice, because that will come once again later on at one stage. But as we reach till here, so I have highlighted a little bit here. Now let us go to the next page. Now I'm writing one more function. One more recursive function. Fun integer n and if n is greater than 0, now this time first I will make a call fun of n minus 1. Then I will print n. Then I will print n. And if I call this function with just value 4, can you tell me what is the output? 1, 2, 3, 4. 1, 2, 3, 4. So you can tell the answer only if you are tracing it, right? So trace this one. Let us trace it. I will trace this one. So when you call with fun of 4, you call with fun of 4. Now, fun of 4. 4 is greater than 0, yes. So what are the steps that it has to perform? Two steps, step 1 and step 2. So it has to perform two steps. Okay, step 1 and step 2. So this is step 1, step 2. Now watch here. First step is what? Function of 3, fun of 3. Then second step is print. But wait, first finish first step. Finish first step, then go to second step. First step is what? Fun of 3. What is that? Function call. So again it will call itself. Again from here it will call itself. Fun of 3. 3 is greater than 0. Again two steps inside. First step, second step. First step is what? Call fun of 2. Then print it 3, but not now. First finish this function 2. It's a call. It will not print. It will not. So this call, again two steps. So it will make a call fun of 1, and printing later it will do. First it has to finish this step. Function of 1. 1 is greater than 0. So two steps it has to perform. First one is call function of 0, and then do printing. But first function of 0. Function of 0 greater than 0? No, not greater than 0. This is stops. So till now the function was just calling itself, calling itself, calling itself. Function was calling itself, right, recursively. At this point it has stopped. Now this has finished, so it will go back to the previous call. It will go back to the previous call. In this call, first step is over. What is the second step? Print 1. So the output is what? Print 1. Right? Then it will go back to the previous call. This is finished. This is finished. So in this second step is what? Print 2. So it will print 2. Then it will go back to the previous call. So print 3. So print 3. It will go back to the previous call. Print 4. So it will print 4. So go back to previous call. So whoever has called this function, it will go there. So if you observe in the previous time also, I have shown you, it will go back. It will go back. So, but while going back, it was not doing anything. But this time, while going back, it has something to do, because after the function call, printing is there. So it is printing, keep on printing. So the output is like this. And if you want to see what is the activation records, how they are created, so let us draw this. This is the code section. So first time, the call for fun of 4 is done. Then call for fun of 3 is done. Sorry. I'll not. Oh, okay. 3 is done. And again, call for fun of 2 is done. Then call for fun of 1 is done. Then call for fun of 0 is done. So when it was 0, this has finished. So the activation record is deleted. It will go back and it has to finish printing part. So what is the value of n in this one? 1 only. All right. So it will print that 1. All right. So if you see here, n is 4, n is 3, right? Actually, I have written the function itself here. N is 2 and n is 1, then n is 0. All right. Got it? Now, one thing. Printing is done at returning time. See, one doubt usually students may have, even when I was a student, I had it, right? See, 4 became 3, 3 became 2, 2 became 1, 1 became 0. Then how 1 is becoming, how this n is becoming 1 once again, how it is becoming 2 once again, how it is becoming 3 once again. There is no n plus plus here. How it is becoming? So actually, how it is working is every call activation record is saved. 4, n value was 4 here. It's as it is. 3 as it is. 4, 2 as it is. 1 as it is. 0 as it is. 0 finish. When it go back, n is there in the activation record. Its value is 1. So for each call, its activation record is as it is there. So when it's going back, it is using the value. So it means all the values of n are actually stored in the activation records inside the stack, right? So they are preserved. So when it's coming back to the previous call, the same call, it is going back to the previous call, the value is as it is there. So n is, sorry, variable n is not created just once in the memory. It is created for every call. All right, for every call it is created. So the point is important. Point is important, okay? For every call it is created. Now, next, same thing for fun of n, sorry. for fun of n. Total calls, how many? N plus 1. Stack size, how much? Sorry. Stack size, I will say n plus 1 only. And what is the time taken for this order of n? I'm not saying big O of n, right? Big O omega is a different thing. Just we are talking about the degree of a polynomial, order of n. We got the, so if you see the number of calls, the time is dependent on the number of calls, right? Sorry. I'll just write f. The time is dependent on the number of calls. F of n is how much? N plus 1. The time taken is f n plus 1. So what's the degree here? N plus 1. Sorry, n power 1. So it's order of n. The time is dependent on the number of calls. So we are, based on that, we are saying, and we got the polynomial n plus 1. Time is n plus 1. So you can also call it as, instead of f of n, you can say time taken for value n is n plus 1. We got a polynomial. And from that polynomial, degree of a polynomial is order of n. That's it. नहीं, Zafar, for value 0 also it will create an activation record, but when it enters inside the function, nothing happens because condition fails. Activation record is created, but printing is not done, further calling is not done. It will get inside the function, but not inside the conditional statement. So, okay, I got your question. You are saying that printing is not done, so we should not say, we should not count that call. So actually, we are not analyzing based on the number of prints. We are analyzing based on the number of calls. So we got the answer as n plus 1. And if you are saying that, no, sir, we will count it based on the number of prints, then it is n, just n. So we said that it's dependent on the number of calls. So we counted the calls. And in one of the call, printing is not done. Okay, so we are not concerned about the printing. So that's what I said now. Will you count the petrol cost also, fuel cost also? Like how you want to analyze, that's your choice. That's your choice. And one more thing, when you say analysis, actually, analysis, see, okay, how I should give you an example. Elevation of a house. Elevation of a house. Every house will have a different elevation. Can you say this elevation is good or this elevation is bad? Or interior of a home, this is good, this is bad? No, that is based on their requirement. This is based on their requirement. So design is never good or bad. That depends on the requirement. Same way, analysis is never right or wrong. It is based on the requirement. Now, when I say this is my home, where is bedroom? You have not taken bedroom at all. Where is a bathroom? Where is a kitchen? You are calling it home. No. So there are some guidelines when you're making a home. So a design will have guidelines. There is nothing like good or bad. You should follow the guidelines. So same way in analysis also, guidelines are there. You follow that one. So guideline is what? So in terms of what you want to do analysis, you can do it. So we did it based on the number of calls. All right, understood this one. Acha, if you do in any way, answer is finally order of n only. Order of n only. So that's how we are interested in degree. We are not interested in minor details. Anyway, chal. Finished. Now, let us compare few things. If you see the previous function call, first printing was done, then call was made. And the stack was as it is. Time and calls were same. And if you see this one, first call is there and then printing is done. And the stack is same. Tree is different, but the stack is same. And output is different, and the number of calls and the time is same only. So main thing is the stack is same compared to that one and this one. When you pass 4, you are getting the same stack. All right. Only the difference is, now I have to explain one more thing here. Listen, I am showing one thing, one important thing. If you see the recursive function, first time this is called, then it is calling this one. This is calling this one, calling this one, calling this one. Now listen, finished. Return, 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 return. Call, 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 call. Return, 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 return. So a recursive function will have two phases. One is calling phase, other one is returning phase. So in this function, printing was done in which phase? Print, then call, print, then call. So first calling phase, printing was done at calling phase. And if you see here, printing was done at which phase? Returning phase, returning phase. So one important thing we observed here is that a recursion will have two phases. A recursion will have two phases. Two phases. Or say times. Phases or times. Phases or times. First one is calling. Second one is returning. And calling is also called as ascending. And returning is also called as descending phase. Ascending and descending phase. So we learn recursion will have two phases, calling phase and returning phase. Calling phase and returning phase. Yeah, Meenakshi, it's a stack, so it is following LIFO. And what's your question? Else it's very... No, it is recursion, so it's LIFO. If the code variables, if it's not recursion, then there is no need of stack. Just one function call. So there are two phases in recursion. One is calling phase and one is returning phase. Now, based on this, we will say that when you have any recursive function, okay, I'll write on the similar skeleton here, n is greater than 0. You have one statement here, statement 1. Then second one is calling function calling itself with n minus 1. Then next statement is statement 2. Statement 2. Now, watch this. अरे तो whatever is here, this will be executed at calling time. Whatever is after the function call will be executed at returning time. This is executed at calling time. This is executed at returning time. Suppose along with the function something is there like plus n or something is there. Something is there. This operation is also done at returning time. This is very important. Sometime along with the function call, we write some operation also. We write it as an expression something. So if expression is there along with the function call, then that expression will execute at returning time. Okay, something is there. We'll see what could be there. So we'll see some examples. But one thing right now you keep in mind that just above the function call, everything is executed at calling time. Then after that is executed at returning time. And if along with the function call something is included, then that is also done at returning time. That's also done at returning time. So these statements are at returning time. This is at calling time. Over. And see, in loop also repetition is done now. Repeat. Acha, in recursion also what is happening? It's repetition. Same as that only. Repetition only. So actually recursion is similar to loops. Similar to loops. But in loop you will have repeat, execute the statement, repeat, execute the statement, repeat, execute the statement, condition fail, stop. There is no return. But in recursion, you have the important thing is what? Returning part. In recursion, you have the strong part of recursion is it is having returning part. All right. So that's the strength of recursion. That's how it's make different from loops. So if you are writing recursive function means you want to utilize which part of the recursion? Returning part of. If you have to use a calling part only, don't write recursion, write a loop. It is easily possible using loop. But when you are writing something at returning time, then it's not easily possible using loop. You need to add something extra along with the loop. What is that? How to do that? Slowly we will see. Just I'll give you a hint here that whatever you can write, you are writing using a recursion, you can convert into loop always. But if it is happening only in calling phase, easily you can convert into loop. If it is happening at returning phase, then you have to add some masala extra along with loop. Okay, is it enough? Okay, so one thing you remember right now, whatever you are writing recursion, that can be written using loop, and whatever you are writing using loop may be written using recursion. Maybe, not always. But every recursion can be converted into loop. All right? Now, that's enough. Now, one thing. Types of a recursion. And all these types of recursion are there in gate questions. Means they did not ask types of recursion, but all type of recursive type of codes are used in gate exams. Okay, they have framed the questions. Now, what are those? Let us look at. Head recursion. I'm just writing head. Recursion comes along with that. So I am using the same function name. Okay, void fun, which takes some parameter n. Okay, I'm using the same syntax here. Skeleton is same. Now, the very first thing is function call. Then after that, whatever the statements are there. So inside a recursive function, the very first thing should be a recursive call. Then whatever the statements are there, that should be followed by that. This is called as head recursion. Okay. Just wait for a minute. Let me finish few, then you can note down. Tail recursion. And in this, I'm writing a same skeleton here of a function here, which is taking some parameter, and it must have some base condition. So I'm writing a base condition. Then all the statements are there. Then finally, a recursive call is made. Now, this is called as tail recursion, a recursive function in which the last statement is a recursive call. Means there should not be anything at returning time. Everything should be done at calling time. Everything is done at returning time. Now, which type of recursion can be easily converted into loop? Tail recursion. Write down same condition for n greater than 0. For I is greater than n, whatever it is, you want to write something. For you cannot, while n is greater than 0, write down the statement. That's all. N minus minus. You can easily convert into loop. But nothing should be there at returning time means just one point. Can I write here something extra along with this? No. If you write, it's not a tail recursion and neither a head recursion, just a recursion. Just a recursion. So this is a special recursion we are talking about, right? Otherwise, just a recursion will say. Especially the very first line is recursive call, head recursion. Especially last line is recursive call, tail recursion. Anywhere in between, just recursion. Just a recursion. Now, next, tree recursion. Tree recursion. Oh, void function fun, which takes some parameter n, and if n is greater than 0, the function is calling itself for n minus 1 and doing some work, and again calling itself for n minus 1, or whatever it is, not just always n minus 1, but just as a skeleton or pseudocode I am writing here. Now, if you observe, the function is calling itself two times, one time, two times. Two calls are there. So if a function is calling itself only one time, then it is called as linear recursion. If it is calling more than one time, then it is called as tree recursion. Tree recursion. Okay. So if it is calling itself only one time, it's linear recursion. Which type of recursion this is? Head, but also linear. Tail, but also linear. Multiple times, tree recursion. Maybe 2 time, 3 time, 5 time, 100 time, as many times it is. It's tree recursion. We call it as tree recursion. So 3 you take, then few more I'll show. So one categorization was when the recursive call is made. So either head or tail. Second one was how many calls are made? One or more. One means linear, or more than one means tree. Linear but head, linear but tail, tree. Is it okay? So now we have to see more recursions. Ah, I'll write down here. Oh, sorry. I'll write down here void fun1, which takes parameter n, and it is having some condition n is greater than 0, and is having something here, and calling function 2 by passing n minus 1. Then void, I'm writing void, not showing a returning part here, which takes parameter n, and as long as n is greater than 1, then here it is doing something and calling function 1 by passing n by 2. Now, I have not given the name. You will give the name. See, function 1. If I start from function 1, from main function, which one I am calling, it depends. So I am calling function 1. So it's calling function 2. Function 2 is again calling function 1. Again, it's calling function 2. Then it is calling function 1. Fun 2, 1, 2, 1, 2. At one time, they will stop. So this is, okay, cyclic. Any other name? No, this is recursion. Type of recursion. Exactly. Indirect recursion. You can say cycle also. Okay, that is your term, but it's called as indirect recursion. Indirect recursion. Cyclic calls, you can say, cyclic calls. But the recursion name is called as indirect recursion. So in gate questions, they have used some questions, given some questions using indirect recursions also. They gave the code and asked you what's the output. See, you'll not find all these type of recursion in any one textbook. Now, from where I have brought this one then? From gate questions. Now, some books will talk about head, tail, over, finished. And in some other book, he will talk only about tree recursions. He may not give the name as tree recursion. So actually, it's not coming from programming language or C programming book. Topic is not coming from C programming book. So the topics are designed based on the gate questions. So you'll not find a single book in which all the topics are present. So listening the lecture and whatever the notes that you are writing, and then revising them by keep on solving the questions. So you can remember the subject only one way, that is by keep on solving the questions. Whenever you are free, open PYQs, look at them. If you forgot anything, try to recall. If you want anything new, just study it further. This is the only way for every subject. This is my suggestion. Okay. So if you are referring notes, then notes means if you are unable to solve, come back and see the notes. Okay. See, if you have kept the notes, no, I should prepare for exam. Okay, it's a little bit ahead now. We will do it later. So don't waste the time like that. So from the moment when you see gate questions, keep on solving them. What are the subject is completed, you keep on solving those gate questions. So they will tell you what you should prepare, what you should not prepare. Questions will tell you. All right, that is the only key. Okay. This is indirect recursion. Over. So you have finished this one. I'll keep it aside. Okay. Now, one more recursion I have to show you. One more recursion. Void fun integer n if n is greater than 0. I am writing the same syntax here. Something is done here. Then fun of n minus 1. Nested recursion. It is calling itself from here, but that result is given to this call once again. Nested recursion. This is called as nested recursion. So many recursions are there. So using nesting of function calls also, they have framed some gate questions. So you should know that this is also possible. But when you see the PYQ, you can solve it. It's not difficult. So don't get scared with so many type of recursion. You can easily solve the question. Okay, because you know how to trace it. You know how to trace it using a tracing tree. You have to do it. So you can do it easily. It's not a big deal. But these are the various ways of writing recursions. Uh, okay. Over. Let us move to next. Yeah. We start from fun one. Fun one called fun two. Fun two called fun one. Back there. So it's not direct recursion. It's indirect recursion. See, fun one in calling itself in another way. Not from here, but from fun two. So indirectly it is calling itself, not directly. Indirectly via fun two it is calling. That's why we are calling it as indirect recursion. Head and tail is a different thing. Yes, you can make that as head, this as tail. That is possible. That's a different thing. So this is based on when it is called. This is based on number of calls. This is based on the way it is become recursion. Not directly, it is indirectly. And this is the depth of calls. Depth of calls. Call inside call, call inside call. So the criteria, category criteria is different for all of them. Just we have seen the names. We have not taken single criteria for defining all of them. Okay, criteria is different for all. Yes, this can be head, this can be tail. Possible. Yes, that's true. That's true. Now, over types of recursion I have shown you. Now, you should know this one. I'll write one function, void fun integer n. If n is greater than 0, print n, call n minus 1, call n minus 1. If I am calling this function fun for value 3, you have to tell me the answer. Draw the tracing tree and tell the answer. Now from here, a little bit of explanation. Most of the time you will have a class work to do. Okay? You have to trace it. So I have not shown you how to trace a tree recursion. It's a tree recursion. But you know how to trace recursion. So you can do it. So you have to tell the output. What is the output? Yes, correct from online. No, check it once again. Check. Yeah, that's correct. That's correct. Uh, yeah, Gupta is correct. 1, 2, 3. It has to do 3 steps. First step, print 3. Output, print 3. Then make first call, fun of 2. Second call also it has to make. I will write it, but we have to do it later on. Fun of 2. I am writing it, but I should finish this one first. So 3 steps. Print 2, 2. Make 2 calls, fun 1, fun 1. First call, print 1, call fun 0, fun 0. Print 1. First call, fun 0, nothing. Second call, fun 0, nothing. So if you see for fun 1, all 3 steps completed. Printing is also done, calling further is finished, calling further is finished. So fun 1 finished. So this call is finished. So go back. In this one, first part is completed. Second part is also completed. Third part, it has to start. So 3 steps in this one. Print 1, call fun of 0, call fun of 0. This one, nothing. This one, nothing. So printing 1 was done. So, oh, so all 3 steps are over. So this is completed. So if you see for fun 2, all 3 steps are completed. So fun 2 is also over. Then it will go back to the previous one. In this one, this step is over, this step is over. 2 steps are over. Third step is start, it has to start. So in this one, 3 steps. Print 2, so print 2. Then call fun 1. So I'll just write F1, F1 because no space. And even when you trace tree recursion, you should give sufficient space gaps here. So you can draw everything properly. Now in this one, first call. So print 1, fun of 0 and fun of huh. See, instead of fun, I just wrote F1, right? So it's okay. But tracing is important. If you now further, this call is made. Now here first printing 1 is done. So this is 1. Now still if you feel lazy, just you can say F of 0, F of 0 also. But trace it, right? Trace and give the answer, right? So this is over. This is over. So this is finished. This is finished. Now it will go to this call print 1 and F of 0 and F of 0. So printing 1 is done. So this is nothing is done. Nothing is done. Over. This is completed. So this function is also completed. For fun 3, all 3 steps are over. So fun 3 is also completed. So 2, 3, 2, 1, 1, 2, 1, 1. This is the output. 3, 2, 1, 1, 2, 1, 1. Over. 3, 2, 1, 1, 2, 1, 1. This is the output. This is tree recursion. What it is doing, just printing. After that, the function calls are made. So whatever the work is done, that's done first. Then after that, function calls are made, and there is nothing in between the function calls. So if you see neatly only these steps, then printing is done before the function call. So it is just like pre-order. Just you can say pre-order. All right. Recursion, but it's like a pre-order. First printing is done, then after that everything is done. Okay. Now, one more thing. In this, see, I was writing output 3, then 2 every time I was writing. Suppose you already have a drawn a tree but not taken the output. Watch here. You have not taken the output. So you can take the output like this. Go from left to right. First you find 3. So 3 is done. So then you find 2. Then you find 1. Then you find 1. Then you find 2. Then you find 1. Then you find 1. 3, 2, no intersection of line. I'm not crossing over any line. Just vertical lines I have drawn on this one and join them. So this belongs to 3, 2, 1, 1, 2, 1, 1. So if you have drawn the tree and you want to see what is printed, then you can see it like this also. All right. Huh? Huh. Yes. All right. Now, next thing. Next thing. Important thing. What is the time taken by this function? So what it is doing? Just printing. So this is taking how much time? Constant time. So this is constant. So the time is dependent on the number of calls. Number of calls. All right. So for 3, total how many calls are made? Count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So for 3, 15 calls are made. Acha, for 2, how many calls are made? 2 means you should stop here, na? You should not go further. 1, 2, 3, 4, 5, 6, 7. See, you have the tree for 3. You can easily give the answer for 2 from that one. So 7. So now you guess for 4, how many calls will be made? Okay, okay. So for n, how many calls are made? 2 power n plus 1 minus 1 calls are made. 2 power n plus 1 minus 1 calls are made. Is it okay? No. Chal. Now watch this. Watch this. If I pass 1, then this will be the only one call. Pass 0, this will be the only one call, right? And here, 2 calls are there. If I call further, 4 calls are included. If I call further, 1, 2, 3, 4, 5, 6, 7, 8. 8. If I call further, in this layer level, how many calls will be there? 16. So this is nothing but 1 plus 2 plus 4 plus 8 plus 16 calls are there. Goes on for n, right? So we want the answer for n. Total how many calls we want? Total how many calls? So this is 1 plus 2 square plus 2 cube plus goes on up to, sorry, 2 power n. It will be 2 power n. Yeah, 2 power n. So do you know this series? GP series, where R is 2. R is 2. So you know sum of this GP series? That is the answer. 2 power n plus 1 minus 1 calls are made. So if you see, this is 2. So 2 power 3 minus 1. 2 power 3 is how much? 8. 8 minus 1, 7. This is 3. So 2 power 4 minus 1, 16 minus 1. That's how we are getting the answer. Is it okay? Understood this one? See, actually, we were supposed to see just the tracing. All right, what is the output? But along with that, we have seen counted the calls also. We so came across this progression series, right? GP series we came across with base as 2, that is common ratio as 2. And the answer is that one, 2 power n plus 1 minus 1. So what is the time taken by this one? Time depends on the number of calls you said. So the time is how much? 2 power n. 2 power n. Is it polynomial or exponential? Exponential. This is exponential. So whenever you have a tree recursion, the time taken by tree recursion will be exponential. All right. Number of calls. Number of calls. Are you comfortable with this? This doesn't belong to C programming, right? But we have drawn the tree, so we have counted also. This belongs to data structures or algorithms. Yes, correct. 15 was correct. 31 was correct. Yeah, pre-order traversal procedure. Yes. For trees, we use that pre-order, but same term I have used it here. Just to relate with that one, I have used the term. This is not exactly known as pre-order. This is similar to pre-order. Over. Now you are familiar with this one. So quickly you have to tell me the answer for this. Void fun integer n, but you should draw it and give the answer. Don't give the answer without drawing, okay? Maybe you know the answer, but don't answer it. See, printing is done in between two function recursive calls. So this is, I can say this is similar to in order. And also I have one more, void fun integer n, and here if n is greater than 0, then first I will call fun of n minus 1, then again I will call fun of n minus 1, then I will say print n. So this you can call it as similar to post order. So for this also you have to tell the output what will be the output when you call this function by passing 3, and this also by passing 3. Tree will be similar, but printing step is at different locations. Previous one was having first printing, but this will have a printing in the middle. This is having printing at the end. I have traced it in short, not detail. So at least you should do this. Never give direct answer. If you give direct answer, 9 times you may give correct, but 1 time you may go wrong. So tracing is very important. 1 to 1, 3, 1 to 1. There, 1, 1, 2, 1, 1, 2, 3. 1, 1, 2, 1, 1, 2, 3. 1, 2, 1, 3. Yeah, 1, 1, 2, 1, 1, 2, 3. Yeah, it's for the second function. Correct. Yes, Kavita, correct. Keshav, correct. Lokesh also give the correct answer. Gupta also given the correct answer. Yes. Uh, Suman, yes, correct. Perfect. Yes. 1, 2, 1, 3. 1, 2, 1. Yes. That was for in order part. Yes. Then you have given Keshava is given for post order part. Yes, correct. See, I will show you one more thing here. This is over. For this one, I have traced. I am tracing that one now. Tracing that one. You have not seen, or I have not shown you how I have done this. I'll just select this one and make it small and keep it here. Watch this. 3 steps. Call, print. So function of, oh, sorry, instead of writing function, I'll just write fun of 3. Call, print. So fun of 2, and print 3. I have filled the level. Next step you watch. Fun1, print 2. Fun1, print 2. I have filled the level. I have not followed this will call this one, then this will call this one, then finish, again call further, finished. I am not doing like that. Level I have filled. Then this one, fun 0, na? So why to write fun 0? It will not do anything. Print 1. Oh, preparing export. Will not do anything, print 1. Will not do anything, print 1. Print 1. Will not do anything, function of 0 and print 1. Okay. Now I'll use different color here and trace this one. Draw a line. 1, 1, 2, 1, 1, 2, then 3. 1, 1, 2, 1, 1, 2, then 3. Okay. Already I have traced this one, so I know how it works. So in a simple way, I have done it. So if you keep on practicing every time, you may find shortcuts for getting the answer. But I have traced it. Okay, always trace it and do it. That's enough. So level by level I have done, and then I have drawn a line and marked the vertical lines upon it. Then I got the answer directly. Instead of writing output every time, I have done it like this. So this is for post order, we have done it. Over. So we have finished different type of recursions, and in that we have seen the tracing of a tree recursion. Okay. And we can see the tracing of indirect recursion, all those things, but that is not much required. When we solve gate questions, that are enough. Okay. So I'll be doing it. Slowly we'll come across them. Now, let us practice few recursions. Okay. I'll write down the code. You have to tell me the answer, what it's going to do. I'll give the same name, void function passing parameter n. If n is greater than 0, return fun of n minus 1 plus n, else return 0. If I call this function for fun of 5, what will be the output? Trace and give the answer. This is not printing, but adding n. No, you can't trace level wise. I have shown you that previous example that already I am familiar with the working. So if you feel lazy for tracing it thoroughly, you can do it level wise also and get the answer. But tracing is important. That was my point. You should not trace level wise. Yeah, answer is correct. No, you should not trace level wise, Varun. You should not trace. I told you, no. I have already done it. I know it. So I have done it level wise. So if you are practicing recursion trees every time, then you can do it faster in this way. That was the point. That was a lazy approach just to encourage you to do tracing. In worst case also you do tracing, because if you don't do tracing, you may go wrong. So you should not go wrong. So just move the pen. That's it. Huh. So in this, you have to learn something. Okay, you have to learn something. I'll trace it. Maybe you have traced and got the answer, but you have to do one observation here. When you're calling a function for 5 for the first time, I'm just writing f. 5 is greater than 0, yes. So what it has to do? Actually, it has to do two things. Make a call and add n. Make it as a separate step, add n. Along with that, just not a call, no? Call plus something more. So that you count it as a one more step. So it will make a call fun of, oh, sorry. I have, oh, undo. Yes. I'm writing f only, no? Huh. Fun of 4, then plus what? Returning time, not now. Returning time. It has to be done at returning time. That's one thing. Now, next is again two steps. Fun of 3 plus returning time. Okay. Then two steps. Fun of 2, then plus returning time. Fun of 1, then plus returning time. Fun of 0, then plus whatever is there is at returning time. Now, when it is 0, fun of 0, watch here. I'm writing it. Yeah. Fun of 0. When it is calling fun of 0, it will not enter here and return 0. So this function returns 0. So it returns 0. So what is the result of fun of 0? When a function is returning something, its own result is that one. Its own value is that one. So this is 0 plus something, right? Now this is over. This is 0. Then plus the result of this is 0. So, okay, I should draw it like this. Okay, that's enough. Now what is this one? Plus what? 1. So this is how much? 1. So this will return 1. So the answer of this function is how much? 1. Then 1 plus this is 2. So the answer is 3. Return 3. So the result of this function f of 2 is how much? 3. 3 plus 3. So this is 6. And return 6. So the result of this function of 3 is how much? 6. Plus this is 4, returning time. So this is 10. So this is return 10. So this is 10. When the function return means its own result is equal to that one. So its own result is equal to that one. So 10 plus 5. So this is how much? 15. So return 15. So result of this function is how much? 15. Result of this function is 15. All right. So this function is same as what it is doing? Sum of n natural numbers. Sum of first n natural numbers. If you observe 1 plus 2 plus 3 plus 4 plus 5. When I gave 5, if I give 6, 1 plus 2 plus 3. So if you observe how it is added, 1 plus 2 plus 3 plus, initially 0 is there anyway. So 3 plus 4 plus 5. And if I pass 6 plus 6, if I say 10 plus 10, if I say n plus up to n, so it's sum of first n natural number. So what this function is doing, this type of question is also important. What this function is doing, this is giving the sum of first n natural numbers. Do you agree with this? Understood this one? So if you trace this one, you can see 1 plus 2 plus 3 plus 4 plus 5 it is doing. That is nothing but sum of first n natural numbers. All right? So have you finished? If you want to take, okay, you have already done it now. Anyway, chal. Now, next. I wrote void in the previous one. Sorry. I wrote void. This is not void. It is returning, no? So it should be int. Yes, that was the mistake. Void fun integer n. Watch here. Watch here. Don't copy. Just watch here. If n is equals to 0, return 0. Return fun of n minus 1 plus n. Is it same thing or different? Same thing. See, earlier, I have first written greater than 0, then do it. And I wrote brackets, then else, brackets, return 0. Properly I have written the code, lengthy code. But first n greater than 0, then do it. But this time I am saying what? If n equal to 0, return 0. Else, I don't have to say else. When inside, if you have written, you don't have to write else. Because if this is true, it will stop here itself. It will not come here. If that fails, then automatically this is else. So you can skip else. Okay? But this code is little bit difficult to read compared to previous one. Right? Perfect? So if n is 0, return 0. When n is 0, return. When n is 0, return n only. Can you say this? But when you read, is it giving you the clear idea that it will be returning 0? Quickly, it will not give you the idea. Quickly, that's it. So when they give gate questions, they will design them like this. When 0 was there, happily you can see 0. You got the idea. You can keep it in mind easily for tracing purpose. Or if you are without tracing also, you can. N means, what is n then? 0. Okay, 0. Then again, what is n? 0. So you have to recollect every time. So this is little difficult to read and understand. Anyway, so int fun of int of n. I'm showing you different ways of writing the same thing, right? N equal to 0. Yeah. Return n equal to 0, 0, fun of n minus 1 plus n. Ternary operator. If this is true, do this, else do this. So in this again, to make it a little confusing, n. If this is true, return. If this is true, return this. Otherwise, this one, this result, either this or that. Same thing can be done like this also. Okay. So for same function, I have given you two more versions the way they can be written. All right. So if you want to copy them, copy this. Is this sum of first and natural? This is also sum of first and natural number. The first one you may be able to quickly answer it, but these two you have to do a little bit tracing, right? Or if you are familiar, you can quickly answer it. So anyway, you get familiar while studying and practicing only. So in gate question, you can easily answer it. Uh, Today also class till 8, 9. Indian Standard Time 8 or 9. 9. We will see, Danish. I'm not sure. But the class will continue up till 9 o'clock. But not sure. Depending on the students here, it may go up to 10 o'clock also. May- Over, finished. Now, I am writing a function here. Int function fun, integer n. If n is equals to 0, return 1, else integer temp, assign function of n minus 1, return temp into n. What this function will do when you call it for fun of 5. I'll help you in tracing part. See, when you call it for 5, what are the steps? Is it equal to 0? If it is 0, it will return 1. Otherwise, what? This is if means termination part. Otherwise, it will do these two steps. So first one is it will store the result of fun of 4 in this temp variable. Then second step is whatever the value of temp, it will multiply with n. Then again here, it will store the result of temp, result of the function of 3 in temp, and whatever the result you get, that will multiply with this value of n. So something multiplied by, okay, here for you, to help you, I am writing this one. Whatever the result is, multiplied by 5. So when you can know the result, when it is returning back, then only you can know. So this is temp assign fun of 2, right? Then also, whatever the result of the temp is, multiplied by 3. Then this is temp t in short. As going deeper, so I'm making it short. So to make it easy to write, multiplied by 2. Then further, t is assigned with f of 0. Then whatever the result is multiplied by 1. Function of 0 is how much? 1. So now it's going to return back. Now it's going to return back. So this is how much? 1. So 1 into 1 is how much? 2. So this is how much? 2. So 2, sorry. Yeah, sorry. 1 into 1 is 1. And this is how much? 1. 1 into 2 is 2. So this result is 2. So 2 into 3 is 6. So this result is 6. Then 6 into 4 is 24. And this result is 24. And 24 into 5 is 120. So this result is 120. So the result of this function is 120. So if you observe, this is doing what? 1 into 2 into 3 into 4 into 5. This is nothing but what? 5 factor. So this function is for finding the n factorial. All right. So the tricky thing is, if you see it any textbook or online, you will not find the function written in this way. I have used a temporary variable, store the result, then multiplying. So you cannot easily read and say what it is doing. Huh. If you start tracing, you can tell the answer a little bit. Okay. This is for finding the factorial of n factorial. Simpler version I have written. I have used the name also, fact, to show its factorial. Here, storing in temporary variable, then multiplying with 10 and returning it. But direct returning. This is the way it is written in textbooks. You will find always like this. Fact of parameter, then fn is 0, return 1, else do this. Over. You have to tell what this function will do. I am giving the name as fun and taking two parameters, x as well as y. If y is equal to 0, hmm, okay, else, hmm, okay. So I will write down like this. Just a minute. If y is greater than 0, return fun of x comma y minus 1 plus 1 plus 1. Else, return x. Trace and tell the answer for fun of 2 comma 3. Answer is 5. If I make it as 7 comma 3, so what the function is doing? Addition of two numbers, x and y. Addition of two numbers. Okay. Return 0. Uh, x. See, that was plus 1. Y is decrementing as many times y was decremented, 1 was added. So y times 1 is added. So y only plus x. That was x. But now this is 0. So x is added how many times? Y times. Adding x, y times gives you what? X into y. So this is for multiplication. Multiplication. X gets added. Acha. What is the starting value of the function from where it will start adding? 0. 0 plus x plus x plus x plus x y times. I'm writing one more function. Int fun integer n if n is greater than 0, print n, call fun of n by 2. And if you call this function by passing h, what will be the output? Till now we were doing minus, 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 but now we are doing divide. Eight, 4, 8, 4, 2, 1. 8 plus 4 plus 2 plus 1. Sorry, sorry. So 8, 4, 2, 1. All right. Now, addition function I have removed. It's not there. Okay. So now, what is the time taken by this function? Hmm. Let us trace it. Trace it. Okay. So when you call the function for first time, you passed 8. Then it has done what? Printing 8 and call itself for 4. Then printed 4 and call itself for 2. Printed 2 and call itself for 1. Printed 1 and call itself for 0. For 0, it doesn't go further. All right. So if you see what is the time taken by this one depends on the number of calls, because simple thing it is doing is printing. So number of calls are how many? For n equal to 8, the number of calls are, sorry. Mm, for n equal to 8, the number of calls are how many? Here I will write down n, like this I will write down n calls. For 8, 1, 2, 3, 4, 5 calls are there. So for 4, how many calls are there? 1, 2, 3. Sorry, 1, 2, 3, 4 calls are there. So for 3, how many calls are there? Sorry. So not 3. For 2, how many calls are there? 3 calls are there. So for 16, how many calls will be there? 6 calls will be there. 6 calls will be there. So for 8, 1, 2, 3, 4. Yeah. So what is the behavior? How do you observe the behavior? Hmm. See, 0 call is extra here. If you see reducing 8, 4, 8, 4, 2, 1, it's getting divided by 2 every time. So 0 is extra here. 0 call is extra. So you can say this you can measure it as 5 and this you can measure it as 4. So 8 versus 4 and 4 versus 3 and 2 versus 2 and 16 versus 5. How do you relate? For n, how many calls will be there? How many calls will be there? Log, no, log n base 2. Log n base 2 plus 1 plus 1. Now if you say include this one also, this is plus 2 plus 2 plus 2. So this is how much big O of log n base 2. This is a polynomial where that we got the time as polynomial. In this, the highest degree term is log n base 2. Log n base 2. Okay. So we could not figure out directly from the numbers here. We could not do it. Could not do it. So I'll show you in a different way. So just you finish if you are copying it. I'll show you in a different way. See, listen to this. 2 into 2 into 2 into 2. This is successive multiplication. 2 into 2 into 2 for k times. Then this is how much? 2 power k. 2 power k. So this is exponent. This is exponent. All right. So if you have a 2 power k, suppose, then divided by 2, divided by 2, divided by 2, divided by 2. So how many times it should get divided so that it becomes 1? K times. It should get divided for k times. K times. Successive multiplication is written in terms of power. Successive division is written in terms of log 2 power k is what? K. All right. See, this was the seed point. 2 into 2 into 2 into 2 into 2. So 2 power k. So this was the seed. 2 power k divided by 2 divided by 2 until it becomes equal to 1. So how many times it should get divided so that it becomes 1? That is written as what? Log 2 power n. All right. Now, see, 2 power n if you write. 2 power n. And if the answer is how much? So wait a minute, wait a minute, wait a minute. N is equals to 2 power k. Suppose n is, this is over. This is over, leave it. Now I'm showing you some other thing. N is equals to 2 power k, right? K is equals to, it is just like n is equals to, n is equals to mm, 5 into p. Then what is p? See, this was in multiplication. When you change the side, division. If it is addition, if you change the side, subtraction. So inverse of multiplication is, inverse of addition is, inverse of power is, I have assumed that you don't know what is log. So I am giving introduction to log. Okay. So what is log? Inverse of power. Power is successive multiplication. So what is inverse? Successive division. Up till where? Up till it becomes 1. Until it becomes 1. So log is successive division. Or in other words, log is inverse of power. So if you bring, see what is this n? What is this 2? What is this k? So what is power? K. What is base? 2. So when you bring that 2 on this side, still we call it as base only. Log base 2. Log n base 2. Answer is what? K. See, if you read it, if you multiply 2 for k times, you get n. If you divide n by 2 for k times, you'll get 1. Or if you divide n by 2 until it becomes 1, so how many times it will be? K times. Understood this one? Got the idea completely? So what is happening in this function? N is getting divided by 2, divided by 2, divided by 2. So answer is what? Log n. Understood? So when division is done, n, log n. When minus was done, n. Anyway, so is it clear? So now we'll practice few things on this one, okay? So just, we are involved in the time complexity now. We are actually doing C programming. So I said that it's not just we will learn C, C, C. When we are touching this topic, we'll learn everything about it, or as much as possible. So whatever is simple, we'll do it. Now, watch this, watch this. Now you have to tell me what is the time complexity of these functions. Okay, void or int, whatever it may be, fun of integer n, and if n is greater than 0, and do something and call fun of n minus 1. What is the time taken by this one? Come on. Watch here, watch here, watch here. Integer fun of int n, and if n is greater than 0, something call f of n minus 2. All right. Minus 2. Minus 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 means order of n. Minus is happening, so it's order of n. How much it's getting subtracted, that's not important. It will go linear only. It will go linear only. Now, int fun of integer n, if n is greater than 0, all right, whatever it is, you'll get order of n only. Now, if you want to really trace it and see, I'll show you. You get the polynomial n plus 1 for this one. You get the polynomial n by 2 plus 1 here. You get the polynomial n by almost 100 plus 1 here. So this is the time function, and this is the time function, and this is the time function. Degrees, degrees, degrees. Understood this one now? So degree is one means linear, linear. As you increase the value of n, the time will increase. That is only the meaning. As you increase the value of n, the time will increase based on the increase of the value of n linearly. That's the meaning. Understood this one? Now you don't have to copy this. Just wait. Int fun, integer n. If n is greater than, okay, 0, usually write 1 anyway. Doing something fun of n by 2. What is the time taken by this function? Log n base 2. Now integer fun, integer n, if n is greater than 1, something function n by 3 log n base 3. Base 3. Understood this one? So if there is successive division. Now, lastly, we are learning about recursions only. Okay, recursions only. One thing you observe. And also we saw the how to find the time also. Okay, by tracing tree, not by recurrence relation. I am not showing that. Okay. Now, one thing if you observe, function is calling itself. It should stop at some point, you know very well. So this is the condition. But from n, it should reach 0. So for reaching 0, it should reduce itself. You agree up to here? N value should be reduced. So how it is reduced? By subtraction. How it is reduced? By division. A value can be reduced either by subtraction or by division or by 3 ways are there for reducing the value. Or else log n also you can do. So for reducing, okay, not decreasing, I'm saying reducing. So this is decreasing, this is dividing. So for changing the value, for pushing it down, putting it down, you can subtract or divide or root or log. These are the possible ways. Now you understood one more thing, you got one more idea now. All right. So we have seen recursion only. Actually, I was all the recursion I was showing with -1, -1, -1, -1. But now I have shown you that even you can do log, even you can do root, even you can do this log and also. By 2 also, by also, divide also you can do. That's what the about the recursions. All right. Now, shall we move further? 8:30 till 8:30. Is it okay? Hmm. But tomorrow 9 o'clock again. Hmm. Because when you are coming from far distance, even I am, for me also it's taking 1 hour, more than 1 hour. So we should spend some enough time, right? So now let me write on one function. You should trace and tell the answer. Okay. Now this is interesting. This is similar to gate question. Not exactly gate question, similar to gate question. Function fun n. Yes. What will be the output of this function? Any, it's not added with the previous function call. It's not added with the previous function call. I have not written anything with fun of n minus 1 plus something. I have not written. C is static. Okay. Let us trace this function here. Let us trace this. When I'm calling with the function of 5, now it has to do 1, 2, 3 steps. 1, 2, 3 steps. So C is a variable. As it is static, so it is created at the loading time and remains throughout the program. So let us make it separate, and that is 0. First step is what? Make that as 1. So let us take it as 1. It is made as 1. Okay. Now calling itself for 4. Then returning will be done at returning time, not now, right? Return. Then again in this, 3 steps are there. First step is what? It will make it as 2. So this is 2. Then calling itself for 3. Returning will be done later on. 3 steps are this. So this will make it as 3. This is a 3. And call itself for 2. Returning will be done later on. So again 3 steps are say this will become 4. And this will 4. So I'm just writing it 4. Then right now, okay, call for what? 1. And returning will be done later on. Then this is what? It will make it as 5, and this is 5. Okay, then this is 0, and for 0 nothing is done, and returning will be done. So 0 nothing is done. Now returning start. Return C. What is C? 5. So this is return here, so this is 5. And in this function called return what? C. What is that? 5. So this becomes 5. Right? Return C, 5. Return C, 5. Return C, 5. So answer is what? 5. No, not 5 times. Every call is returning C. Returning C, what is that? 5 only. No addition of C with anything. It's not 5 times. See, it has given the... See, watch here, watch here. Now, return, this function is returning first time what? Nothing. Nothing. Function is 0, nothing it is returning. Then it is returning 5. Am I taking in some variable here? Adding with C? No, I'm just leaving it. Nothing. Then the last call 5 will be returned to the caller 1. From here, if I call main and say print, fun of 5. Fun of 5. So last call value will be returned to main. And this returns I am not taking anywhere. You are thinking or reading it extra, actually. Reading it extra. See, the return result I'm not taking any variable. I'm not adding with C at all. See, now once again, read it here, freshly. Increment C, increment C, increment C, increment C, increment C, 5, stop. Increment C. Now do what? Return C, return C, return C. What is C? At the end, 5, 5, 5, 5, 5, 5, 5. C, 5, C, 5, return 5, return C, 5, plus, 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 stop. Now return, return, return. 100 times also return also, it will be 5 only. Over. Clear now? Clear? Sure. Overriding. Overriding you have done. Overriding means, huh? Hmm. What will be the output of this one if you print? Actually, we were talking about printing only every time. So final output of this one is what? 5. Previous returns, where they have gone? Nothing. So it will not be 5 times 5. 1 time 5 only. Chal. Next. Anyway. Int function fun integer n integer oh sorry static int c assign 0. Now if n is equal to 0, return 0, else C++ return function of n minus 1 plus c. Give the answer for fun of 4 as well as fun of 5. For both you have to give separate answer. Fun of 4 separate, fun of 5 separate. Then I have a question what this function is doing. That's my question. No, you can't say no output, Kavita, because finally it is returning to the caller function. Yes, correct. Yes, I have already explained that. Yes. For this, you will give correct answer. You give correct answer. I am asking you to find it for 4 as well as 5. So final answer also you will be giving correct. Not 20. No, you did it for 25 and you took the answer till 4. You have to do separately for 4 separately and for 5. Don't take the answer from 4. No, not 10. No, you have to go. No, no, no. Gupta, you have stopped little bit before. F of 4. C becomes 1. F of 3 plus whatever the value of C at that time. And then C becomes 2. F of F of 2 plus whatever the value of C at that time. Then C becomes 3. Then F of 1 and whatever the value of C at that time. Then 4, C becomes 4. F of 0 plus whatever the value of C at that time. F of 0 is how much? 0. So now the result of this is how much? 0. Plus C value is how much? C is static. C is static. So for all the call, there is only one C. And right now it is having value 4. That's what the trick here is, because it's static. So this is 4. 0 plus 4 is 4. And the return result is 4. 4 plus 4 is how much? Again, C is 4 only. This is 8. Return result is 8. 8 plus 4 is how much? 12. And the return result is 12. 12 plus 4 is how much? 16. And this return result is 16. So for f of 4, fun of 4, the answer is 16. For fun of 5, the answer is 25. So for fun of n, the answer is n square. Right? It is adding n for n times, actually, if you see indirectly. N for n times. So this function is finding square of a number. All right. So because it is recursive and with the help of static, it is doing by successive addition, finding a square. All right. So tomorrow we'll continue with, now we will solve few more, then we'll learn one topic, that is pointers, then again recursion, arrays, then along with recursion, operators, then along with recursion, normal code as well as with recursion. In that way we'll be doing it. Okay. So we'll stop here for today. We'll continue in the, or shall I continue up to 9, or is it okay? Okay. So tomorrow it will be till 9 o'clock. Okay. हो गया 8:30 to 9 के बीच में बुलाने को बोला था। ठीक है, तो बच्चों का पोस्ट कल 9 तक था।